today I want to talk about the evolutionary conflicts of inbreeding. This is fundamentally a talk about mating preferences and how they produce conflicts, let's say. The basis of this talk, or the crux of the modelling effort, was introduced by Jeff Parker in his classic book chapter in 1979, where he introduced the idea of sexual conflict, or at least the phrase. And I guess just to get it out of the way early, the type of sexual conflict I want you to think about here is the interlocus kind, conflict over the outcome of an interaction, right? And so Parker's model is all about inbreeding and whether inbreeding is actually favoured by selection. So if I take my indiscriminate lecking shorebirds here, I want you to think about the decision that this female on the left can make and what the genes she carry might code for here. So from the perspective of a focal gene, I guess to use Andy's language from earlier, if this female carries an allele and she chooses to mate with an unrelated male, we can say that using a very simple gene copy counting technique, that she's going to pass on n/2 allele copies or gene copies to her offspring. And the over 2 just appears because we assume this allele or gene is present in a heterozygote. If instead she breeds with a related male, then from a direct fitness perspective or a direct gene propagation perspective, she'll pass on n/2 times by this 1 minus delta term, where delta is inbreeding depression. So you can think of this as the loss of offspring production caused by the expression of deleterious recessives. And if we just stopped here, it's super obvious that inbreeding shouldn't invade this population, right? If delta is somewhere between 0 and 1, this quantity on the bottom will always be smaller. But the thing is, the problem doesn't end there. We need to also count the gene copies that are transmitted by her related mate to their shared offspring. And I don't want you to get concerned, or at least I want to allay your fears that there's some double counting going on here, because you can see that these n/2 terms appear twice. There isn't double counting here because the offspring they produce are shared, but both the male and female transmit alleles to their offspring, right? And that's why it appears on both sides. And of course, here we've got to moderate the expectation for gene propagation by some relatedness coefficient, and that's what this R term represents. So if the sum of these two gene transmission pathways exceeds the n/2 term, we would expect inbreeding to invade this population. Now, let's think about the male perspective. So if instead males control the outcome of mating interactions and they express inbreeding acceptance, inbreeding avoidance alleles, the situation is similar, but it has some crucial differences. So here, if a male breeds with a related female, we get exactly the same setup as we got in the previous slide. In terms of, this is the gene copies that flow from this interaction between the breeding attempt of males, a male and a related female. If instead the male chooses not to inbreed, to avoid inbreeding with the related female, she can go on and she breeds with an unrelated male, and she'll pass on n/2 times R gene copies from the perspective of what the male decision produced. So this is very similar but slightly different, because here now the unrelated breeding attempt is moderated by R. So what Parker then did was he said, okay, let's find inbreeding depression thresholds above which inbreeding can't invade and below which inbreeding should invade. And in the female case, you end up with this R over 1 plus R term, and in the male case, you end up with this 1 over 1 plus R term. And if we plot these, this is what you get. And so just to quickly walk you through this plot, we have some sort of relatedness coefficient here. I want you to think about genealogical relatedness. And in this space here, inbreeding will invade if females control the outcome of the interaction. Above this line, inbreeding is no longer beneficial from the female perspective, but it is, in this region, beneficial from the male perspective. And then above this line, it's detrimental for both sexes. So Parker described this middle space as the zone of sexual conflict, where the fitness interests of the two sexes differ, or I should say inclusive fitness interests of the two sexes differ. Now, this model is really simple. One thing that's crucial for how this model works is it's assumed that there are no mating costs for the male. Everything is purely additive. It's an extra mating attempt that the male otherwise wouldn't get. It doesn't replace any subsequent matings, whereas females are assumed to be purely monandrous. If they inbreed, it absolutely replaces any outcrossing opportunity. The other thing is we treat inbreeding depression as a fixed parameter here. But of course, as inbreeding progresses, you would expect this thing to be dynamic. Inbreeding should evolve as inbreeding progresses through invasion. The thing is, all of these things have been done. These extensions have been made. And the long and the short of it is that Parker's model really holds up really quite nicely. You can put intermediate sex roles in there. You can do this not with an inclusive fitness approach, but with a direct fitness approach. And you tend to get the same answer with the same assumption set. So I'm really happy with this model as a very informative, I guess, or a very powerful toy model from which we can build upon further. And what exactly I want to do in terms of building upon this is take an implicit assumption of Parker's model, which was that these alleles or gene copies are present on autosomes, and expand that out and say, okay, let's think about different genomic regions beyond just those autosomes. And so with Hannah and Arvid, we started thinking about this question. And we figured we probably could identify potential regions for conflict. And here I like Francisco's definition, and this is what we use as well. It's where the inclusive fitness interests of different, I'll call them genomic regions, there's a disagreement here, or they differ at least. So this is what we end up with for females. And I show you this just to say this thing now looks different, right? How we actually get there, I'm going to spend the next couple of minutes explaining. So we have our direct transmission if the female inbreeds. We have the indirect transmission if she inbreeds by her related mate. And then we have the alternative scenario of direct transmission if the female outcrosses. But there are some new terms here. So first of all, we need to think about the total class reproductive value of, and here by class, I mean the sexes, because this will weight the value of the male and female transmission pathways. There's also this fraction in here, and we've got these F coefficients, which are very loosely meant to be interpreted as inbreeding coefficients. We'll talk a little bit more later about why this is a very, very loose use of this term. But really what it's capturing is this assumption that this allele is present in as a baseline, a heterozygous diploid. But of course, this is not true for all types of genomic regions. So we need a general way to handle this for cases where, for example, something might be hemizygous. I want to say that inbreeding depression here, despite we're going to move between different genomic regions in terms of where inbreeding preference alleles are found, but we're not going to change how inbreeding depression works across these scenarios. We assume it's this totality of recessive deleterious mutations across the entire genome relevant for any case. And then the last thing, which I don't have an arrow for, but I should have pointed out, is our relatedness coefficients. These also are not going to change across genomic regions. We're going to let reproductive value and what I'll call ploidy dilution do that work. I want you to think of these as genealogical or like pedigree calculated relatedness coefficients, because that's actually what, we can go out and measure quite a little bit easier. And the other thing I should say is this is all inspired by Hamilton's life for life idea of the relatedness coefficient. So a lot of inspiration came from that. Okay, so what do I mean by total class reproductive value? I don't think I have to spend so much time on this because we had really nice introductions to this concept yesterday. But how I'm using it is the probability an allele or a gene copy, I guess, in a distant future population descends from a particular class in the present population. Classes here, I mean sexes. So if we take an example, let's think about a gene on a W chromosome. We were thinking about birds earlier, right? So I want you to think about W chromosomes and Z chromosomes here. So the male fraction of the population has 0 reproductive value for a W-linked allele, right? They simply don't carry this chromosome. So here we can use this as a bookkeeping trick. What about Z chromosomes? Well, males transmit the Z to zygotes of both sexes, whereas females only transmit Zs to sons, right? And so what this works out to do is that the male fraction of the population has a total reproductive value that's twice that of the female fraction of the population. And so we go through and do this for all of the major, I guess, genomic regions that we can find in animal populations. I'm not going to tell you all what they all are now, but we've done it. And it will produce some results that I'll show you soon. Next, there's this dilution of diploidy is what I call it. This is how I think of it, at least. And this is purely a bookkeeping trick, and it's quite hacky, but it's effective, I think. So here it's this fraction, right? And what Hamilton was interested in were how does reproductive value and things like this in regards to the sex ratio work when you have a haploid sex and a diploid sex. And so he said, okay, if you have a diploid and it's outbred, then let's set these inbreeding coefficients to 0. And then you end up with the usual haploid setup. You get a half, and this is where that n on 2 came from that I showed you at the start. If instead the system is haploid in a particular context, then we can set this inbreeding coefficient, and this is why it really isn't an inbreeding coefficient. We can set it to 1. And really what we're trying to say is that there's no dilution of diploidy here now, right? The males very faithfully, no, for a Z, females very faithfully transmit their Zs onto their progeny, whereas males don't do that if they're outbred, right? There's another allele, or there's another gene copy at the locus, and we don't assume anything about that if it's randomly sampled from the population in an outbred context. Now, if we were to stop there, from the perspective of a Z or an X in an XY system, we would say, actually, this completely cancels out the disproportionate reproductive value that you find in the case of the Z in males, in the case of the X in females. Because of this, yes, they carry 2 gene copies, but it's diluted. So this thing cancels. Except if inbreeding affects the invasion of inbreeding. And by this I mean this inbreeding coefficient, which we assumed 0 in a diploid, right, can take the value, any value between 0 and 1, if inbreeding builds up homozygosity in the lineages that are doing inbreeding. So it's not a population level inbreeding coefficient. It's very specific let's say, to the families that are doing inbreeding. So inbreeding alleles can be extremely rare in the population, but locally abundant, producing homozygosity and breaking that exact cancellation. And this, in cases like that, with very frequent inbreeding, you need to do this. This means that you get different expectations for the invasion of an inbreeding allele on a Z chromosome versus an autosome. Okay, and this plot is kind of the culmination of everything I've been saying here. And it's very similar to that plot I showed you from Parker earlier. So instead of sexes here, now we have genomic regions. And so let's walk through this slowly. So on the bottom here, this is the level of inbreeding depression we predict that can be tolerated if inbreeding acceptance alleles are on W chromosomes or on maternally inherited cytoplasmic chromosomes. And it's actually nothing. There's no level of inbreeding depression that can be tolerated, and that's because the male transmission pathway is completely worthless for a W chromosome. If we then move up the plot, we can find that this is the threshold for the X in the most extreme situation of inbreeding. Very, very rapid inbreeding makes that inbreeding coefficient 1, and it means that reproductive value, or the difference in reproductive value, dictates whether you get invasion of inbreeding acceptance alleles there or not. And it's why we get a difference between the X and the autosome. The Z, here again, we show the most extreme case, and a higher level of inbreeding depression can be tolerated in that case there. And then finally, up here I've got this cyto-P, and what this is it's completely hypothetical. But it's if you had a cytoplasmic element that was transmitted down the paternal lineage rather than the maternal lineage. And in that case, there's no level of inbreeding depression that stops the invasion of these inbreeding alleles. And in that, let's say, slightly fanciful scenario, I would predict dire consequences for this population. So that's the female side. I'm a bit cognizant of time. So this is the male side. And you can see that it flips just like the Parker thing. But you get similar regions where, yes, you get inbreeding alleles that are favored on some chromosomes and they're absolutely not favored in the same selective conditions on other chromosomes. The other thing to say here is that I hope you can appreciate that there's also strong sexual conflict and strong interlocus sexual conflict if, say, you took an allele on a Y chromosome and in a male and contrasted it with allele on an autosome in a female. So I want to come back to these Parker thresholds that I showed you earlier, here updated with the terms that I've included in the model now. And what I want to show you here is that what is causing this conflict is fundamentally a difference in the value of paternal transmission relative to total transmission that occurs from this interaction. Chromosomes that disproportionately value paternal transmission have very high inbreeding thresholds. Chromosomes that disproportionately disvalue it have very low inbreeding thresholds. And it's the same case for males and for females. So here, this is a reproductive value. Well, let's do it for males. This is a reproductive value weighted value plus here the extra bit you get if ploidy dilution is abated by frequent inbreeding as a fraction of the whole value of the interaction. So it's really about this paternal transmission value. And I just wanted to finish, this is the last slide, by saying that I think this is it's a case I think it's a new case at least of what I think is a well-studied but simultaneously understudied broader form of intragenomic or within organism conflict. And I think these are the conflicts that arise when the value of transmission by different classes, sex here is the easiest one to think about, differs between those genomic regions. And I would unite this with a couple of different phenomena we have out there. For example, actually, I think most of these people are in the room, except for Bill Hamilton. I think this is a similar sort of conflict as what's generated by mating preferences for selfish sex chromosomes, any form of conflict over sex ratios, and also the cytoplasmic male sterility, that conflict with autosomal genes, I think is the same sort of conflict again. And in a paper that Arvid and I, along with Yamo Erten, but particularly with Gaurav Athreya and Shikara Bhatt, we have submitted to JEB at the moment, we make the case that this is not like the conflicts generated by assortment asymmetries, like you would get with maternal imprinting. It's not like the conflicts you would get with segregation asymmetries or segregation distortion. It's all about transmission asymmetries, and it's that value of the two pathways that matters here. And in my head, these are the three major forms of internal evolutionary conflict. And I think there's great potential to study this form moving forward as well. So thank you very much.
So in the interest of time, Tom, I'm going to have you come up right away, and then we'll have a super quick question. Yes.
All right. First of all, I'd love to talk. I want to combine this talk with Pavitра's previous talk in the sense that looking at sex determination transitions, would you expect, given the different interests of the X and the Y, that when they arise newly, that this leads to divergent evolution in new sex chromosomes as far as inbreeding loci are concerned?
Yeah.
Yes or no is fine.
Maybe.
Yeah. Yeah, I would lean towards maybe. That's potentially the most non-committal answer I could have given.
We can discuss.
Yeah, let's think about that afterwards. I wouldn't want to overstate inbreeding as a mechanism. But I think these thresholds that we derive and Parker derive are not prohibitive for inbreeding acceptance, but I think many times in nature we'll see that they're exceeded. So is it a universal mechanism that causes or stops something from happening? I wouldn't say that, but it's something we always need to consider, I think. So, yeah.
Let's thank Tom.